Hi, everyone. Today we are going to talk about conservation of angular momentum in collisions. So first we have these two disks, right? Two cylinders. One is rotating, one is not. The one called number one with moment of inertia one is rotating with an angular speed omega one. Before the second cylinder with a moment of inertia of I2 not rotating is dropped onto the first cylinder, and the two cylinders begin to rotate together, right? So it first asks, should omega increase, decrease, or stay the same? And then it asks us to derive an expression for omega final. So intuitively, we're going to think that omega final is going to have to decrease from our knowledge of linear momentum, right? Imagine one object that is moving hits a stationary object. If they continue moving as one mass or as one system, I guess as one object, I don't know, whatever. If they continue moving as one mass with the same velocity, then you will add their masses, but the velocity will be slower than it was before, right? So we're going to intuitively say that this should decrease, but our expression should prove this. So our expression is that initially, I guess we'll start with L initial equals L final, right? So you've got the I1 omega 1, right? Because angular momentum can equal the moment of inertia times the angular velocity. So that's the initial angular momentum because the second cylinder isn't moving. Now, in the final case, you have both I1 and I2 are both moving at the same omega final, right? So that you would clump those together. Now, if we divide that, we can solve for omega final. Omega final is I1 divided by the sum of the moments of inertia times omega 1. Now, the way that this proves that it's going to decrease is because as a fraction, the denominator here is bigger than the numerator, meaning it is less than 1. Meaning if the bottom of the fraction is bigger than the top, it's less than 1. And if you multiply anything by something less than 1, it's going to decrease. So this proves that your angular velocity is going to decrease as these two objects come together. Okay. Now the next says find the ratio of the final to the initial rotational kinetic energy. So this is asking for K final divided by K naught. Okay. Now this is going to get kind of complicated. So first, let's solve our K final and K naught. First, K naught is pretty simple, right? That is 1/2 I1 omega 1 squared. That's pretty straightforward. Now, if we're going to do K final, that's a little different, right? K final is 1/2 I1 plus I2 times omega final squared. But we did just get an equation, an expression for omega final. Okay, so we can take this expression and we're going to put it in right there and we're going to square it. So this then says that Kf is 1/2 times the sum of moments of inertia times I1 over the sum of moments of inertia times omega 1 squared. Okay. Now, to simplify that, let's say that this is 1/2 I1 plus I2. Now let's square everything. You've got I1 squared over, now the sum is squared times omega 1 squared. Now we can see that here we have, these can cancel once, right? So that's going to simplify a little bit, but we are still left with kinetic final equals 1/2 moment of inertia 1 squared divided by the sum times omega 1 squared. Okay. Now we are going to divide these, which is, again, going to be some intense algebra. So if we've got K final divided by K initial, okay, you've got 1/2 I1 squared divided by I1 plus I2, omega 1 squared divided by 1/2 I1 omega 1 squared. Things that can cancel, the omegas and the 1/2s, those can go away, right? So that leaves us with the fraction I1 squared divided by I1 plus I2 divided by I1. And that's just disgusting. You should never work with a fraction like that. So let's multiply by the reciprocal. Okay? We've got our standard fraction there times 1 over I1, right? That we know what to do with. And that leaves us with this ratio. That is the ratio of the first moment of inertia divided by the sum of the moments of inertia, is the ratio of the final kinetic energy to the initial kinetic energy. This is also showing that kinetic energy decreased here, right? We conserved angular momentum, but we lost energy in the process. And that is because kinetic energy was lost as the second cylinder sped up, or as the first cylinder slowed down. You can think of it both ways, right? So as the first cylinder is rotating, right, and then it drops down this stationary one, they're not going to immediately catch and slow, and I1 will slow down and I2 will speed up, right? There will be this moment in time where I1 and I2 are skidding across each other as I1 slows down and I2 speeds up until they both are moving at the same angular velocity, right? So until that time, there is friction, and that friction is taking away some of the energy of the system because it is a non-conservative force. All right, a next one. This one's a doozy. So we have a ballistic collision in angular world. So a wooden cube with side length S and mass M sits motionless on a frictionless table attached to a light rigid rod, light meaning massless, rigid meaning it's not going to bend, that pivots at the other end. So you can see that right here. Okay? The cube's center of mass can be assumed to be located at the end of the rod. A bullet traveling normal to the rod and parallel to the horizontal surface embeds in the cube. I do want to bring that up here. I want to mention that a bullet traveling normal to the rod, okay, that means that it's parallel. So if the rod is laying on the table, the bullet comes at it at a perpendicular angle. That's what it means traveling normal to. And it is parallel to the horizontal surface of the table, so it's not coming down at an angle or up at an angle. It is horizontal to that, parallel to it. So it asks us to derive a few things. We're going to work through these one at a time. First, it wants us to derive an expression for the moment of inertia of the cube bullet system after the collision. So if we look at this, we want the moment of inertia of the system, right? We want the moment of inertia of the cube and the moment of inertia of the bullet. Okay? The rod, again, has no mass. It's considered a light rod, so we're not going to include its moment of inertia. So there is the moment of inertia of the cube, moment of inertia of the bullet that we'll consider, and then we'll put those in. Now, the moment of inertia of a cube we haven't used before, but it is 1/6 mass the cube times the side of a cube squared. This is a cube, right? Not some rectangular prism, not some long rectangular box or anything. This is a cube, right? So all sides must be the same length. That's why we use 1/6 ms squared. Now that's a prefab, meaning that that is for a cube that is rotating about its center of mass. But the center of mass, if it were right here, it is rotating over here. So that means that you need to consider the parallel axis theorem. So parallel axis theorem says that you should you should add md squared. Okay, add m. Now the d represents the distance between the center of mass of the object and the new axis. And that distance is length L of the rod. So that will be mL squared. Now the bullet, there is no prefab for that bullet that we have that we're working with. So we're going to assume it's a particle. The moment of inertia of a particle is the mass times the radius from that particle to its axis of rotation squared. So that will be little m for bullet and the length of the rod squared, ml squared. So that means that our total moment of inertia for the system will be 1/6 big M s squared plus big M L squared plus little m L squared. So that is the expression for the moment of inertia of the cube bullet system after the collision. Now, 1A, there is this what if scenario, right? Does this change if the rod has mass? Yes, it does. So then we would also consider the moment of inertia of the rod, and this is a rod pivoting about its end. So that's not 1/12, that is 1/3 mass of the rod, L squared. So if that were the case, if this rod did have mass, that doesn't complicate our problem too much. You would just take that and tack it on the end there. Not too much to add. Now, number 2, derive an expression for the conservation of angular momentum of the cube bullet system. So what we'll do here, section that off. Okay, number 2, we want the expression for the conservation of angular momentum. We want the initial and the final angular momentum. So I will remind you that angular momentum can equal RMV or I omega. So initially we just have the bullet moving, but the bullet is moving in a complicated way, right? Every second that it moves, right, the bullet is here, okay? That's its radius. But now it has moved here. That's a new vector. And then it has moved here. That's a new vector. And then it has moved here. That's a new vector. So it's very complicated to narrow down what is that R value that we would use for RMV. But remember that we can use the perpendicular idea, right? You can either take the perpendicular radius times the mass velocity, or you can take the perpendicular velocity times radius and mass. So we'll do it just that. If the velocity is in this direction, right? The perpendicular radius would be right there, length L, right? So our perpendicular is L, so that means that our initial moment of inertia would be L mv, mass of the bullet, velocity of the bullet. Then final, okay, that is where we would take the moment of inertia of the system, which we just took all that time writing down. So let's go ahead and use it. That would be 1/6 ms squared plus big M L squared plus little m L squared, all times its angular velocity omega, right? And that would be the expression for the conservation of angular momentum within this system. Okay. Now, part 3 is a little bit more complicated. Derive an expression for the fraction of kinetic energy lost after the collision. So what it's asking is the delta K over K initial fraction, right? This will tell you the approximate percentage of energy that was lost. So if we want to find that, we need delta K. Delta K is K final minus K initial, and then divide by your K initial. The K initial is going to be relatively simple. K initial is just 1/2 mass of the bullet, velocity of the bullet squared. Okay. Pretty straightforward. However, afterwards, K final, right, you've got 1/2 I of the system times omega squared. Now, you can approach it in this way. However, we can also say that this is 1/2 mass of the system times the velocity of the system squared. That would be a V final. Okay? Now, we're going to use this approach to find our final kinetic energy. Okay? Now, first, we need to find that VF. Because if we don't, then our velocities aren't going to cancel out to give us a nice ratio. So I'm going to find our VF over off to the side here. So this stems from the fact that L naught equals LF and that L equals RMV and I omega. So we already established that LMV is the initial angular momentum. Right? However, the final angular momentum can be described as L m plus m times v final, right? There's nothing wrong with this because our tangential velocity is easily defined in this system because this is not one solid, rigid object that's rotating. It is one bullet and cube system that is rotating about a massless rod. So this is not too big of a stretch to make when we're doing this problem. To find VF, we're simply going to divide. Okay, those L's are going to divide out. So what you get is little m divided by the sum of masses times V equals V final. Okay? We will take this and we're going to put it right there, and then we're going to square it. So for our KF, let's see, what room do I have? Okay, so we have 1/2. The mass of the system is big M plus little m, right? Sum of masses. Then our VF that we just solved for is m over sum of masses times V, but it's all squared. That complicates things, right? So what we'll do is we will square this, right? That's squared. That quantity below is squared, and then the V is now squared, right? And just like before, that will cancel one of those, giving us the equation 1/2 little m squared divided by sum of masses times V squared. And that's our final kinetic energy. We're not done though. Remember, we need delta K divided by K naught. So we're going to take the final kinetic energy minus the initial kinetic energy, then divide it by the initial kinetic energy. So let's take all of that into account. We have final kinetic energy 1/2 m squared divided by m plus little m V squared minus our initial kinetic energy, which was 1/2 mass of the bullet and its initial velocity squared, divided by the same 1/2 mv squared. Okay? Now, dividing by 1/2 mv squared allows us to cancel out those v's and the 1/2s, but we can't just get rid of one of the masses because of that subtraction there, and because it's because of the fraction there, and because of the subtraction. So this becomes little m squared over, let's stay consistent, big M plus m minus little m divided by little m. Now what I'm going to do here, this is just my take on it, the easiest way to do this algebra. Algebra can be done in various ways. So if you have a better way of thinking of your algebra in your math brain, go ahead. But I'm going to multiply by the reciprocal. Got little m squared over big M plus little m times 1 over little m minus little m divided by little m. Whoops. So all I did is multiply each of those terms by the reciprocal, which would be 1 over little m. That cancels one of those, and mass divided by mass is going to be 1. So this leaves us with little m over big M plus little m minus 1. Now that minus 1 we can turn into a common denominator, right? By using the big M plus little m. So we will subtract big M plus little m divided by big M plus little m. It is 1, so that's legal. So now let's write all this out. You have little m minus big M minus little m, right? That minus has to distribute, don't forget, divided by big M plus little m. Those little m's are going to subtract out, and all you're left with is negative mass of the block divided by the mass of the block plus the mass of the bullet. And that is your ratio of the kinetic energy lost after the collision, right? That's the fraction that was lost. The negative here simply shows that there was a loss of kinetic energy. And then the rest of it, the ratio of masses, that is your actual relationship between the kinetic energy lost and the initial kinetic energy that we started with. So that is how we can do those problems with this cube bullet system. Now, if we had numbers, these answers might have a little bit more meaning, especially that expression for the fraction of kinetic energy lost. But we don't have any numbers, so that is what we're left with. Now, next, we have something called physics Sudoku. So physics Sudoku is a fun puzzle way to solve some of our problems. And just to show that if you have a certain amount of givens, that you're actually able to solve for a lot of things in a specific scenario. So here is our scenario. We have a 2 kilogram disk going 3 meters per second. And this is all on a horizontal table. We're looking from a bird's eye view. So this disk is going 3 meters per second, and it strikes a motionless 1 kilogram stick, as you can see there. Okay? Strikes the 1 kilogram stick. Okay? The moment of inertia of the stick about its center of mass is 1.33 kilograms square meters. After the collision, the disk is traveling 2.33 meters per second. As you can see in that after image down there, it continues in a straight direction. The surface is frictionless and horizontal with no external torque. Now, for the elastic collision shown, write 3 general equations and 3 detailed equations for conservation. So we'll do linear momentum, angular momentum, and energy conservation. I don't know if I'll be able to fit this here, but we're going to give it a shot. So for linear momentum, okay, that is P initial equals P final, right? But for the detailed information here, right, our initial momentum is, I'm going to use a little mass for the disk and a capital mass. All right, so our initial momentum, if we use those M notations, right, and they also give us specific notations for the velocity, right? The disk initial velocity is VDI. The disk final velocity is VDF. The stick's final velocity is Vs, and it has an angular velocity omega. So I'm going to say that our initial momentum was the mass of the disk times the velocity of the disk, right? Now our final momentum would be mVDF plus the mass of the stick times the velocity of the stick, right? So that is our conservation of linear momentum. Now for angular momentum, we have L initial equals L final. But what is our initial angular momentum? We have a disk traveling in a straight line. Well, remember that L equals RMV and I omega. Okay, so for a particle moving in a straight line, we can use RMV to describe its angular momentum. Now we do have an R here, right? There is a radius from the velocity vector of the disk to this meaningful point, which is the level at which the stick has its center of mass. So that is a meaningful radius. We're going to use that radius. We have R, mass of the disk, VDI, equals R, mass of the stick, VDF. Okay, those are the angular momentums of the disk. Now, for the angular momentum of the stick is going to be different. It has a moment of inertia, and we are going to use I omega to show that it has its own angular momentum about itself. You can't really use RMV for a solid rigid object, because what would you use for R? I guess maybe you could use the radius of the object. It gets kind of messy there. So if you have the moment of inertia, use the moment of inertia equation. Okay. Now, energy conservation. This, again, since it is on a flat horizontal frictionless table, there is no friction or non-conservative energy, and there is no gravitational potential energy. So we're just going to use kinetic. So let's start over here. We have K initial equals K final, right? But what are our initial and final energies? Well, the disk is the only one moving initially, so you've got 1/2 mvdi squared. Okay? But now that's going to get split up into all different ways. The disk still has its own kinetic energy. And the stick also is moving, right? It also has its own velocity. So it has translational and rotational kinetic energy. So we will show that by saying that it has 1/2 capital M velocity of the stick squared plus 1/2 I omega squared. So now we'll, instead of taking the translational and kinetic energy and the rotational kinetic energy and splitting them up, we'll keep them in the same equation. Something you can't do for linear and angular momentum. Those are our general equations for conservation and detailed equations for conservation that we're going to use. Now, for the Sudoku. This is an intimidating data table, but I'm going to walk you through it. This is actually a powerful tool if you have a complex scenario to see what all you can actually solve for. So again, I'll read the question. We have a 2 kilogram disk going 3 meters per second, strikes a motionless 1 kilogram stick as diagrammed on the previous slide. The moment of inertia of the stick about its center of mass is 1.33 kilograms square meters. After the collision, the disk is traveling 2.33 meters per second. The surface is frictionless and horizontal with no external torque. So first, enter your givens and cross out irrelevant boxes, things that are not conserved. So for example, we've got x's on the velocity and angular velocity, right? Those can't be conserved. So it doesn't really matter what the total velocity of a system is, because these two systems are moving separately. It's not like they stuck together. So adding their velocities means nothing. So we will mark those out. We also know that the stick before has no motion, right? It is sitting stationary. We know that the disk will never rotate, so it will never have angular velocity or rotational kinetic energy. We also know that the disk started at 3 meters per second and finally, after the collision, is traveling at 2.33 meters per second. Those are our givens. That's all we have. The rest is mass and moment of inertia. I do want to point out that our momentum, angular momentum, and our kinetic energies also have a total to them. Those we will total up because they are conserved. If you add up the the momentum of both of them, that will equal the momentum of the system, right? Like we showed here. Add them up, that's meaningful. Add them up, that's meaningful. Add them up here, also meaningful, right? So those we will actually keep open. I also want to note that the translational and rotational, their total box is not sectioned off because we're going to combine translational and rotational. All right. Now, first, we're going to figure out the length of R, right? So before we move any further, there is a fundamental variable that we're missing, and that is R. That came up in our angular momentum section, right? We have this R in our RMV, but we were never given R. What we can do is we can solve for R, and it's going to be key in solving this puzzle, right? It's basically your missing piece. If you don't have that piece, you'll never finish the puzzle. So we do know that the moment of inertia of a stick rotating about its center of mass is a 1/12 mass times its length squared. Okay? And the length of the stick is 2 times the radius of the stick. So we could say that this would be 1/12 mass times 2r squared, which would be 4r squared, right? 2r quantity squared would be 4r squared. This comes out to 1/3 big mass times its radius squared. And we also know that this equals 1.33 kilograms square meters, right? So we can actually solve this. We know that also that the big mass of the stick is 1 kilogram, so if we multiply or divide it, it's not actually going to matter. So R equals 3 times 1.33, and you take the square root. 1.33 times 3 is 3.99, which is basically 4, and the square root of 4 is 2. So we're going to say that the radius is about 2 meters. Okay? That is our missing piece, and now we can go on with completing our puzzle. First, we will solve for the conservation of momentum. Then we will solve for the conservation of angular momentum. And then finally, we will solve for the conservation of energy. So, first, we want P naught equals P final. Okay. First, let's find P initial. P initial is the mass of the disk times the velocity of the disk, which is 2 times 3, which is 6 kilogram meter per second. Right? So that 6 goes right here. You can total that up right now and know that that is 6 right there. And since momentum is conserved, that 6 will also go down here. Okay? Now, that's our initial momentum. Now we want our final momentum. So if we take that guy and we are going to manipulate it, we know that it's got to equal 6 kilogram meters per second. Okay, and our final momentum, like we wrote before, is m VDF plus big M VS, right? The mass of the stick times the velocity of the stick. You can see that we wrote that right here. All right. Now, we have all of these. We have the mass of the disk, velocity of the disk, mass of the stick. We just don't have the velocity of the stick. So let's solve for it. If you take, let's see, 6 minus m VDF divided by mass of the stick, which is 1, you'll get the velocity of the stick, which is, the final velocity was 2.33, right? So you've got a mass of 2 times 2.33, which would be 4.66. So 6 minus 4.66 divided by 1. That will give you 1.33. I guess we could say 1.34. So 1.34 meters per second is the velocity of the stick. So that can go right here. Velocity, stick, 1.34. Okay. Now we can find the moment, the momentum of each object. Okay. So what is the final momentum of the disk? Well, we know that it has a mass of 2 and it has a velocity of 2.33. That would give us a momentum of 4.66. So that would go right there. And the final momentum of the stick, we have a mass of 1, a velocity of 1.34, giving us 1.34. What do you know? 1.34 adds up to 6, right? So there are several different ways that we can go about this, but we are slowly filling in the data table. Okay? Now, that was our momentum part. Now let's do our angular momentum. Okay? I'm actually going to go up and go over our angular momentum once again. Initially, we start with Rm VDI, the radius times the mass of the disk times the initial velocity. That will equal the radius times the mass of the disk times the final velocity plus I omega. Right? Just want to go over that real quick. So let's do L initial equals L final. L initial will equal Rm VDI. Our radius is 2, our mass is 2, our initial velocity is 3. That gives us an angular momentum of 12 kilogram meters squared per second. That's not right. Is it right? Yes, yeah, that's right. Kilogram meters squared per second. All right, so, oops. Let's go up here. You have a initial angular momentum of 12. Plus 0 is 12, and we also know that down here you will have 12. Now, if we know that the final angular momentum must equal 12, that means that we have R, M, BDF, which we have all of those, plus I omega. We don't have all of those. We do not have our omega, right? So let's find this. First, you can take 12 minus R, M, VDF divided by I. That will equal your omega. Okay? So we have 12 minus, let's see, we have 2 times 2, which is 4. 4 times 2.33. That will come out to 9.32 divided by 1.33. Okay, once you put that in your calculator, that comes out to approximately 2 seconds inverse. Okay, so we can go ahead and put that up here, 2. Now we can actually take this 9.32, right, and put that up here. Now for our angular momentum of the stick, that would be I omega, right? So you take 2 times 1.33, that would give you approximately 2.67 kilogram meters squared per second. So right here, you would get 2.67. Yeah. You go 2.67. There you go, right? So 9.32 plus 2.67 gives you approximately 12. We are off by 1/100th, but that is really darn close. Okay, so that covered everything on our part 2. Scribble that part out. Now part 3 is 1/2 mv squared or 1/2 I omega squared. We have our 1/2s, obviously, our m's, our v's, our i's, and our omegas. So this is just going to be plug and chug, right? So for our translational kinetic energy initially, right? KT for the disk initial, 1/2 m VDI squared. That will come out to 1/2 times 2, which is 1. Then you've got, 3 squared, which is 9. So you've got 9 joules. So that means you have 9 here, plus 0, 0, 0. You've got a total 9, which you can bring that total 9 down below. Now, if we continue on, our translational kinetic energy for the disk final, that would be 1/2 m VDF squared. That I can't do in my head. That you get 5.43 is what I'm getting, 5.43 joules if you square 2.33. So that'd be 5.43. That goes right here, 5.43 in our translational kinetic column. Now we can get the translational kinetic energy of the stick. You've got KT of the stick. That would be 1/2 mass of the stick. That's 1. The velocity of the stick squared. See, the velocity of the stick is 1.34. So we have 1/2 times 1.34 squared. I get 0.90 joules. So let's go ahead and put that up here. 0.90. We could just subtract those two numbers from 9. If we do that, we get 2.67. So let's see if we're right. The rotational kinetic energy for the stick is 1/2 I omega squared. So that'd be 1/2 times 1.33. And omega, the angular velocity was 2. So that would be times 4. We can do that. That would be 2.66, right? 4 divided by 2 is 2, times 1.33 would be 2.66. And we just predicted that it would be about 2.67. So again, we are only off by a factor of 100. So that's how you can fill in this kind of data table and show that with these complex problems, such as this, right? You are given very little information. You have their masses, the moment of inertia, and an initial and final velocity. But you're not given any momentums, angular momentums, or kinetic energies, but you can find all of that as long as you have this radius, right? That was the missing puzzle piece. As long as you have that, you're able to do it. But using our little data table here, we're able to get all of those values. All right, that wraps up our conservation of angular momentum. And in our next video, we're going to tackle gyroscopes.